Finite and Lattice Bootstrap.
Okay, thanks. Thanks for everyone for being here, and thanks for the organizer for this nice workshop. I'm Zechuan from Confining Institute, where I'm a postdoc. And today I'm going to talk about the Finite and Lattice Bootstrap, or Finite and Lattice Yamil's Bootstrap, with collaborated with my PhD advisor, Volodya Kazakov. The paper was just appeared last month. So first I put this picture here to clarify the terminology bootstrap here, because from my knowledge, half of the non-English speakers think the bootstrap is just a shoelace, but it's actually this. Yes, so this bootstrap method by the usually by equation functions, they are usually called lattice bootstrap or matrix bootstrap. And it's pretty new, so there is not really a lot of literatures yet. But here I list some of the literatures. Interested audience could refer to these papers to go through the history of this area. Here I don't have I don't have the time to give a very complete track of the history. And here, by bootstrap method, we mean that bootstrap solving the theoretical physics problem by the optimization theory. Especially in our bootstrap community, semi-definite programming, or SDP, plays a crucial role here. This is one of the simplest example of SDP by Mathematica, actually, if you look at the documentation of Mathematica. So here, you have two variables subjected to some semi-definite condition, and then you can solve with minimization or optimal solution very efficiently. More generally, this is one formulation. Sometimes people call it primal formulation, or sometimes they call it dual formulation. But basically, you are minimizing some linear combination of the variables, and the variables they are subject to some semi-definiteness of the matrix condition. So as here, there are some let's say n to n times n matrix, real and symmetric. Okay, how this works to solve our physics problem? Well, there is the schematic how it works. As pointed out by someone last week, that this framework, it is more properly called as correlator bootstrap because it is related with, some people also use it to do the bootstrap of the quantum system. So better use correlator bootstrap to be more general. Here we are minimizing or maximizing some correlator because correlator is basically our physics observable, subject to the kinematical equations, dynamical equations, and the positivity conditions. Dynamical equation, usually here there are some Schwinger-Dyson equation or some quantum equation of motion. Let's take an example to see how it works. But this example is already a bit complicated. So for the first step, we are limited to some very low length cutoff. Yes. So here is a UN lattice gauge theory defined by the Newton action. So there is no fermion, pure gluon. And here our goal is to bootstrap the one plaquette array defined here. So we put a normalization so that when it is basically free, it's one plaquette is one here. How it works? Well, how it works begins with the Martinko-Migdal loop equation on the lattice. And this is basically the Schwinger-Dyson equation. So as you are usually doing that, you are doing an infinitesimal shift of the measure. Oh, no, infinitesimal shift of the variables on one link. And then due to this is a Hard measure, so this keeps invariant, and the full equation, it is 0. And you expand it, you will get the following equation. You expand it, and you need to massage the indices.
So, sorry, but 1 plus I epsilon, you mean 1 plus I epsilon times a Hermitian matrix?
1 plus I epsilon times, epsilon is a Hermitian matrix. Hermitian matrix. Any infinitesimal Hermitian matrix. Yes, schematically it is this way. Some single trace plus lambda times the original Wilson loop we are varying, and the double trace. Let's use some picture to do some illustration. So this is a single trace variation. We are adding some plaquette to the original Wilson loop. And the double trace, how it factorized to double trace, it only appears in your original Wilson loop. There are some overlapping links. Let's use some more concrete example to have a look. This is a simplest example. That is one plaquette. You are varying a link. And then this is 2 dimensions. 3 dimension and 4 dimension, you have more direction to vary. So yeah, for both for the up direction and the down direction, you have both this plaquette and the flipped plaquette. So you have these 2 terms and these 2 terms in pair. And the original one, there is no double trace term. So this is all the Markov double loop equation for the simplest example. Another interesting example is we call the backtrack loop equation. So due to the unitarity, here this backtrack is identical. It is equivalent to identity. But when you are taking the variation, it gets non-trivial because you see there is overlapping, so there will be some double trace, but double trace is 1 times something else, so it's still a single trace. And it got cancelled with the original Wilson loop. So this equation is actually independent of the coupling. It is true for any coupling. So this makes it more or less kinematic, less dynamic. Okay, regarding the positivity condition, here is one example of the positivity condition. By this, I mean there's other examples. If we have time, we can go into that. So this is the simplest example, Hermitian conjugation. So that, well, it comes from basically this simplest idea that for any operator, O dagger O is positive indefinite. But you can expand O into some sum of, let's say, alpha I and omega I, AB. Omega I, AB, I mean some Wilson loops here. Then, because this is for random O, then you can, this equation, actually, it is equivalent to some alpha dagger and alpha, larger than 0, any alpha. And then, mathematically, this defines the positive semi-definiteness of the N matrix and Nij. Yeah.
Right? Blue is not in the deal.
Yeah. Use white.
Use white. White
chalk.
chalk.
Oh, sorry. Let me repeat it. But where is the chalk? Yeah.
Sorry, you said Wilson loops. It's Wilson path. Wilson
Yeah.
path.
This open index is we call it, yeah, Wilson path. Yeah, let me repeat it. We can do some expansion of any operators in some basis of Wilson path. And yeah, this is equivalent because this is for any O. So this is how the positivity condition appears. So where is the semi-definite positivity appears. Okay, this is the lowest order because you are taking the Hermitian conjugation. So you are taking the inner product here by the W dagger W. So what you get 1 on the diagonal. And off diagonal, you get the 1 plaquette because you are taking these 2 paths. The result is pretty trivial because this is positive semi-definite, means that your UP is smaller than 1. But it gets less trivial when you are taking into a bigger basis. So you are taking some Wilson lines starting from 0 and end at 0. Here I put a truncation length 4. So they are basically still bending around the 1 plaquette. But they are open indices. You take the inner product, you get 1 on the diagonal, but off diagonal, you get some Wilson loops up to length 8. Okay, this already enables us to do something. So this is already some example of the Bootstrap. We have 2 equations we just showed. these two equations, this is less dynamical and this is with a coupling. And if you have very sharp eyes, you can see that there is actually 6 Wilson loops in the previous matrix. This is a 9 times 9 matrix, but yes.
Where does the rank of the gauge group show up here? Does it? Or?
Yeah, good question. For the moment, it doesn't appear because this is very low order. So this means that our bound will be true for any un. But take care that SUN there is some subtlety. This is UN.
Lambda is G squared N.
Yes, this is a Tohoft coupling. Okay, 6 variables subject to 2 equations, so you have 4 free variables. Here is our previous example of the SDP. So you can maximize or minimize any Wilson loop among these 6, and you can have this, for example, the 1 placket. So lower bound, it is still somehow trivial, larger than 0, but upper bound, you get some dynamical upper bound. It is already non-trivial. And as pointed out just a moment ago, this is true for any n, actually.
So you quote the result for lambda equals 2.
Yes.
Isn't there a result for any lambda?
Of course, we will show it later. So this is just for illustrative purpose. Yes. Yeah, so this looks very nice. So that it seems that it works for length equals 8, so we can generalize it to maybe 8 meetings. And we can measure all the data of the lattice Yang-Mills theory very precisely, and the lattice QCD is correct. But life is always not so easy. The first thing is that we mentioned the double trace, but here, due to the link, they don't overlap. The double trace doesn't appear, so we are not bothered by that fact. But for longer Wilson loop, it appears. And yeah, there is overdeterminedness of the loop equations, which means that they are not all independent. Some already implies the other. Theoretically, this is not a problem, but numerically, this is somehow problematic. And there are more positivities I didn't mention. That is, there is a reflection positivity specialized to the lattice system. As it's very, very well known that QCD has a reflection positivity. And the matrix, also, this is one of the other very important construction that we cannot go very far because the matrix size grows exponentially. And I mean, the complexity of the SDP already grows some power law with the size of the matrix, and then the matrix size grows exponentially. So this, as the length goes up, it gets very, very hard. Okay, so let's look at the multi-trace variable problem first. Multi-trace, the lowest order, it should appear here. So you are doing the variation on this link, and the single trace, the linear variation, we already explained, so we will not repeat it here. But from this variation here, you can see that this, the double trace correspondence of this Wilson loop is actually some double trace of one placket another, the nearest neighboring Wilson loop. And for the large n situation, this is not a problem because we know that we have large n factorization. The double trace is factorized to the product of single trace. Well, it's factorized, but this makes our loop equation nonlinear by this step. But there is some technique we can deal with it. We use the relaxation method. If we have time, we can go into that. we can go into the detail of that method. But for the moment, we assume that it is already get over, and we can get some nice upper bound and lower bound. This result, I think, is 2 years ago. So that you have the upper bound and lower bound as you increase the Bootstrap cutoff. You have a shrinking allowed region. The dot in the middle, they are the Monte Carlo results. So some of them they are from Andrea and from Mike Tepper, they are Monte Carlo simulation, and the dashed line, they are the perturbation line. But the topic today is the finite n. So we move step further and don't stop there. So finite n, so we have seen that the double trace, it appears. But all the double traces are not independent from each other. there is also the equations between the double trace. And then you do the variation of double trace, you got the triple trace. And it seems this story doesn't stop. Here, this is how you get the double trace. You do the variation, similar variation, but here with some additional factor of the multi-trace. And what's the result? The result got more general. In addition to the familiar two term before, and also the splitting, because the double trace is some kind of splitting. You also have the so multi-trace, let's say M trace variable. When you're doing the variation, you also got M-1 multi-trace variable. That's the story. And this is a formula, but they are pretty technical. I don't want to spend too much time into the technicality here. Yeah, but what's worth noting is that Fg here, this is some factor I used that when it is special unitary group, it is 1, and when it is 0, it is unitary group, because special unitarity brings into some technicality there. So some terms, they don't appear for unitary group. Okay, so, but there is further simplification. That is, actually, it doesn't get that bad. The trace variable, it got truncated. For example, for the 2 times 2 matrix, as a simplest example, you have these equations. You must have this equation. Why? Because epsilon tensor is a totally anti-symmetric tensor. But you don't have enough indices. You are 2 times 2 matrix. You don't have a third index. So it must be 0. This looks very trivial. But if you expand the product of the epsilon tensor into some delta tensors, then you can write this equation as some trace relations here. So the conclusion is that for any 2 times 2 matrix, any 2 times 2, they are not necessarily the same. They are not necessarily unitary. You have these trace relations here, triple trace into double trace. But for the special unitarity group, we have further reduction here. The first equation is somehow obvious. That is, for SU2, for identical matrix, you can always diagonalize it as lambda inverse, and you can verify this equation. But less non-trivially, this is more general, that for any U and V group element of SU2, you have the double trace factorized into single trace here. The derivation of it is a bit technical, especially the general situation, so I won't go into the detail here. But this conclusion is general. That is, for any SUN matrix model, the truncation at the multi-trace, it is at n-1 instead of n. This is general. For example, SU3, you have the following factorization of the triple trace, any triple trace into the double trace. So what's the result? The result is that SU2 lattice Yang-Mills theory, it also closed on single trace variables. Here is some examples. And I especially pick this example because it brings to some redundancy here. So here are some double trace. I add a backtrack here to join these two groups. But here, before using the trace relation, they are not joined yet. You see, this double trace, they are not nearest neighbors. You can factorize it by this way, by adding this backtrack, and also by adding this backtrack, you get some also Wilson loops. What does this mean? This means that single trace Wilson loop, there is some redundancy in the SU2 lattice gauge theory. Okay, substituting the trace relation for SU2, you get the specific Markov-McDowell loop equation for SU2 on the single trace variable. And then you can reproduce everything we have done in the latter. How is the result? This is a 2D, and for SU2, of course, where the SU infinity, it was firstly solved, I think, by Gross, Witten, and also by Wadia in the last century. And here is convergence. So yeah, this is more clear. So we will focus on this plot because SU2 is exactly solvable. And these are the upper bounds. They are how far is the upper bound from the exact result? We see this is a very clear exponential convergence. So this is length 8, 12, length 8, 16, and 24. Well, this is very quick calculation because this is 2D. I think the whole plot it could be done in several minutes. Yeah.
So the exact, you went too fast. The exact result is the red curve?
Yes, the black dashed line in the middle. And the red, because they are very close, the red is the upper bound and the lower bound. They almost coincide with each other.
It's like 0.1% somewhere in there.
Okay.
Yeah, I would say
But-
less than that because the worst situation is less than 1%.
So these, the red curve is the upper lower bound? Anyway, it's what you get.
Yes, here is the upper and the lower bound. But
Okay.
for this plot, it's the upper bound minus the exact value.
Okay, but you say, but how much work did you have to do to get these values?
How much effort?
Yeah.
Well, because this is 2D, this is very.
I know it's simple, I'm just wondering how much.
I think it's several minutes, very quick, very quick. This is almost instant.
But how many, what size?
What size? The size of the SDP.
Oh, the length of the loops probably.
Yeah, the length of the loop, they are length 24. At most.
24.
Yes.
So 24 by 24,
Not 24 by 24, the maximum,
Oh, no, the maximum,
the
okay.
biggest.
all loops. How many are there?
A lot, I think. I think in the order of 100,000.
100,000.
Yeah, around that 10,000 to 100,000, I think in that order. But there is really much more in the 3 and 4D situation.
Of course, I'm just trying to get some feel. So, and did you say 2 or 3 minutes on a laptop?
Yes, this is laptop.
For you?
Yes.
If I was doing it? It would
Code and
But, what?
just press enter and it. Well, it depends on your computational skill because some of it is some combination to construct the SDP is some combination of Mathematica and C because sometimes Mathematica got not that efficient, so it is I write some C code and link it with Mathematica, so it got very fast. Compared with the previous result on the large N, actually the speed up is actually 2 orders of magnitude already. So yeah, really there is technically there is some very hard effort there.
Yeah.
So,
Yes?
do you, in 2D it's also quite simple to get the string tensions in units of lambda. Do you?
Well, 3D we did it. Yeah, we did some try there. Yeah, we will go to that point.
Yes. And did it converge as well here into?
Yeah, the convergence is limited by the length of the Wilson loops. We are actually we will be calculating it using the Cruz ratio. I will show it later. Yeah.
For this plaquette, the SU2 and SU infinity in units of Troft coupling, how much do they differ? Are they very close?
Okay. Yeah, I will. But
I'm just asking about 1/n² correction.
They differ by something like 20%.
20%.
Yes. I mean, I have the plot.
So it's
We
not
can
like
look at it.
it's not like very close.
Yeah, it's not very close. Well, I have the plot actually. We can show it later. Yeah, this is 3D. 3D here. Yeah, this is the same bound. So I think I don't need to repeat the Bootstrap process. But the dot here, because there is no exact solution here, the purple dot. Let me put a zoom plot. The purple dot, they are also the Monte Carlo data by Andrea and by Mike Tepper. So we see that actually for 3D, even this is the non-solvable situation, the Bootstrap bound still gets some decent convergence. I would say it's already within the 3rd digit. This is the physically interesting lambda already. And also
just to maybe add the word, because all these points here, for example, in the previous plot, are precisely the physical window where you can measure something when the radius, correlation radius is not too big and not too small.
Yes, and finally there is a 4D result. The yellow dot and the purple dot, they are both Monte Carlo data, and the dashed line, they are some strong coupling, weak coupling, perturbation expansion. Again, the
Is this the roughening transition? Or the transition
no,
is
there is no phase transition. It's a
Okay,
crossover for SU2. The phase transition appears for SU5, I think. SU5 is some first order, yes. Okay, yeah, so this is the red dot. Unluckily, this is for length 24. Unluckily, we only got 3 pairs. And for the lower bound, there is already we see some numerical instabilities. So the lower bound, they are not so trustable, I would say. Yeah. And for the implementation of this Lmax equals 24 is something huge. Even after solving the loop equation, there is still 200K free variables. So initially, I think it's about 500K, something like that. And this is the SDP matrix, they are 40 matrix, and these are the size of the matrix. So it takes like 1 terabyte of memory on a single machine with 32 cores and 25 days to finish 1 point. So this is some comparison finally with some large N result. So we see that even for the same length cutoff, it indeed converges much better than the large N. So we already changed the normalization so that at the same lambda they are comparable with each other. And this is 3D and 4D. 4D here is very clear that U infinity there is a first order phase transition. Yeah. Okay. Finally, the string tension. This is something we finally done. That is because our length is finally limited. We are using the 2x3 plaquette. 2x3, 1x2, 2x2, 1x3. The crucial ratio to calculate it and compare with the Monte Carlo result. The blue dot is our result, and the brown dot, this is the Monte Carlo result also by Andrea and by McTaper. And beta, when beta is small, beta and lambda, they are related by this transformation. So that when beta is small, which means that the lattice spacing is more bigger. That means even in 2x3, we are close to the asymptotic region. We see that our result and the Monte Carlo result, they are very close. But for very big beta, this is still very far from the
When you
asymptotic.
mean your result, you mean the bounds are so close together, or that's the upper bound? Or?
Yeah, we are picking the solution. We are reading the solution directly from the optimal solution. We are reading the Wilson loops from the optimal solution because either you take upper bound or on the lower bound, their value doesn't change a lot. Yeah, they are in some very tiny physics window.
So there's some error bar there.
Yes, there are some error bars, but
You
they are
can't
not.
see on this plot. You can't see them.
Yeah,
Or
they are in the third digit. You can distinguish a little bit, but very little bit. Yeah. Okay. Finally, I don't think I have a lot of time, and we will go into this one plaquette model.
Sorry, coming back to the reason then for the difference between two determinations, if you're saying that.
Yeah, you mean the difference here?
Right.
Yeah, because we are using some our plaquette. They are not big enough. They are not in the asymptotic region. They are some very small size. Still some very small size, especially for big beta, where small size we are really far from the asymptotic region. Yes, so this is one plaquette model. Here we just want to show that our SU2 story can be pushed to SU3, U2, and maybe U infinity here. In the SU3, you need to really deal with double trace. And here there are some examples of the double trace positivity. I will just show the result because if you know this model, it is also physically interesting because it captures the two-dimensional lattice Yang-Mills series, single plaquette dynamics. So actually, they are the same value for 2D Yang-Mills and 2D lattice Yang-Mills and this one matrix model. And this is U infinity and U3. So you see that they are, I mean, the exact values, the black dashed line, they are they are not coinciding with each other. And also U2 and SU2. SU2 is what we basically what we solved on the lattice, but this is just solving the one matrix model. Okay, final remarks. So the first remark is about SU3 lattice gauge theory. So what's the difficulty? Is it some difficulty in principle, or can our story of SU2 generalize to SU3? I would say from my current understanding, the difficulty is in terms of coding, because you need to write some code to systematically generate this double trace Wilson loop. But for the computer itself, after you finish the coding, it is around the same order of magnitude, I mean the complexity. Because why? Because at any length cutoff, the single trace variable, they have a dominant number. There is not really a lot of double trace compared with a single trace. So it's fine. And I really think that we can do at least as good, almost as good as SU2 for SU3. So the second mark is integrability of the large N lattice Yang-Mills theory. This is some byproduct of this project. So what does this mean? This means that usually we find in the loop equation, the solvability of the model is already captured in the loop equation. For the solvable model, you have a lot of loop equation, but there is very few free variables. Sometimes there is only one free variable. But here we find that SU2, they have much less free variables than SU infinity, which means that SU2, at least it is more, it hints that SU2 is more solvable than SU infinity. But SU2 lattice gauge theory in 3D and 4D, I think there is no evidence that it is some solvable theory, considering that the 3D easing, it is not solvable. So SU2, I don't think there is any evidence it is solvable. So this has some hint that large N Yang-Mills, maybe it is indeed not that integrable. So the remaining three, there are some prospects. The first one is coarse graining. Coarse graining means that our bootstrap, they are still limited very locally. And to go to some very big Wilson loop, maybe we need to do something very similar to the DMRG, that is do some coarse graining, because not every UV detail, they are important. If we can come up with some way to get rid of this UV detail, that will be very beneficial and push this framework much further. The sign problem. There is some hint that this bootstrap method can get over the sign problem, at least sometimes, because the emission positivity, it is correspond to the sign problem with Monte Carlo simulation. When there is a sign problem on the Monte Carlo side, we lose some positivity. But as long as we still have enough positivity, it might work. Because, for example, the reflection positivity, or even other more mathematical positivity conditions, as long as we have enough of this may work. And finally is...
Sorry, so you imply that you can do this with theta term also? This is some open problem for the moment. So this is reflection positivity. And there is also other positivities. I'm thinking that if you can implement them, because even if your measure is complex, there is still some positivity here. Yeah.
But that's just a hope, right?
For the moment, that's a hope.
Because the problem with the sign problem, well, you can get trapped in totally the wrong regions.
Right.
So if you, you're not getting an exact solution. There could be many exact solutions. If you can manage to get enough positivity conditions, you are getting no, rigorous result in some sense. Conceivably.
I'm not, this is some prospect. I'm not promising too much about it. Yeah, but I got some hint that this might be possible.
So are there examples, many examples where you can make rigorous theorems?
Not examples on the lattice side, but on the quantum system side.
But I mean, for these optimization questions in general.
you
Presumably,
mean
in some
some-
cases, you can prove that this converges.
You mean some proof this convergence?
Right.
I mean, you are not talking about sign problem.
Well,
Yeah, indeed, sometimes you can prove it.
For one matrix model.
Yes, for one matrix model, we can prove it. And also, there is some recent result by Min-Jae Cho. He proved that the previous result on the bootstrapping the lattice easing theory, it is converged to the exact value. Yeah. So in some situation, you can prove it. But currently, it's still case by case. So if the model is simple, you can prove it by the simplicity of the model. It's not a general proof that this works. Yeah. For example, for the large n Yang-Mills, we don't have any proof. Yeah. Okay. Yeah. The final comment is about the continuum because lattice breaks the symmetry. For Bootstrap always like more symmetry as possible. So if this could be done in the continuum correctly, it might be much more powerful. Okay, that's it.
Let me add maybe one comment here. That of course we have obvious drawbacks with respect to the Monte Carlo. Our contours are the length of our Wilson loops are limited, and as you saw, for example, on the computation of string tension, we don't get as good result as on the lattice. But we have also some advantages. For example, we have the full table of Wilson loops up to a certain length. This is a little advantage with respect to Monte Carlo. We really give these loops with exact margins. And for example, to measure some correlators, again, for Fermat, we have this sign problem, but to measure some correlators, you multiply sum over loops with the weights, with fermionic weights, or just bosons with e to the length weights. So it could be just directly computed in principle, which we didn't do. We are slow,
you have a
but-
lot of those things. You said you have extra all loops, right?
Yes.
So that's a fantastic number.
Yeah.
What, as far as string tension, have you figured out what useful physical information you can extract from them? Yeah, what do
String
you-
tension is not the best for us, but maybe, for example, the condensate, which is the sum of loops pinned to a certain point, this could be done, and we didn't do it. But we can measure, for example, the condensate, the sum over loops.
What do you mean, the condensate?
I mean, you have, for example, psi bar psi condensate.
You
Then
mean the
you simply
vacuum
sum up over
expectation
loops.
value?
Hmm?
The vacuum expectation
Yes,
value.
vacuum
varies.
expectation. You
Oh.
may try just to sum over loops, and
Hmm.
this is, I think, a good quantity for us. But somehow,
Yeah, no, it's a fascinating question. What would be good quantities? You have, 10,000 loops.
yes, but
You're not interested.
it invites to
10,000
think,
numbers.
what can we extract
What are
from
the-
this huge information?
Exactly. But that doesn't get it.
Oh, there are some sources.
Lattice gauge theorists, I mean, people who do Monte Carlo presumably have thought about this too, no? What to extract aside from just the string tension.
Mhm, mhm.
Computing psi bar psi condensate makes the most sense for massless fermions, not for infinitely massive ones.
Yeah, that maybe.
So you need to add all the massless fermions to the game.
That's true, but. So
You're just saying you want to compute the web for all loops passing through a point. I'm not sure what. That's not psi bar psi condensate, right?
Oh, with small masses, maybe.
No, but then you have to add dynamical fermions.
No, these are just fixed,
But-
infinitely massive. They don't move. You don't have a kinetic field. Have you actually tried to include dynamical fermions?
Actually, of course not yet. We are slow. But for example, there is the following maybe naive thought that since we don't have actually multi-loops here, in SU2, all these internal loops can be in principle connected to the main loop, and you always have a single loop in some sense, even if you have the dynamical fermions. Maybe this idea can help to compute it with dynamical fermions. You see what I mean? You have in principle you have multi-trace because you have internal loops, but since Zechuan showed that all of them are just a single loop, maybe one can resum in this way. I don't know.
But is there any problem in this general scheme of including dynamical fermions? Does it just go through?
No, but then you have to write if you just blindly apply the Schwinger-Dyson equations, you will get sums over big loops. Sure. And then it's a very difficult equation. In principle, you can.
Yeah, I think it works. But still, you are limited to some very UV quantities.
Probably it will be not very efficient. But I say that maybe one can just use this huge library of loops to compute this kind of dynamical fermion quantities, or at least the dynamical bosons maybe.
That's what you would. That's the way. That's the way you would proceed.
One day.
Yes. Okay.
Just a comment, I mean, it would be interesting to compare just the Kreutz ratios at finite sizes with lattice data. I mean, you don't have to extract the string tension. You could even compare these.
Yeah, that's an excellent point. Yeah, this definitely could be done. There is also some higher corrections to the cruise ratio that you can take into account.
And concerning fermions would be the idea, I mean, you could do some kind of hopping expansion or something where you express the determinant in terms of loops, but this would then also be expansion around infinite mass. But maybe this could go in a direction where you can handle this.
Yeah, regarding the fermion, I think the best way is still just directly bootstrap the dynamical fermion. Yeah, I don't see an instant difficulty, but yeah, the same problem is here and also in the with dynamical fermions. You can bootstrap some Wilson lines by some two fermions on the state, but they cannot be very long. That's the only problem.
The dimensionality in which the gauge theory lives, that's the complexity of the number of paths that relate these Wilson loops. Like you can go in different directions on the lattice.
Yes.
So your matrices of the constraints just gets much bigger with dimension.
Yes. For the 4D is, I mean, 2D, 3D, and 4D, they are totally different scale problem. 2D is like instantly got the result. 3D you take 1 day, and 4D you take like 1 month. But this is still truncated. For the 2D, we didn't lose any information. 3D and 4D, we already do some truncation. So we are not very full SDP yet.
About integrability, it would be incredible if somehow just Wilson action gives you on the lattice an integrable. It's like really a lot to ask for.
You mean it's unlikely to be?
Yeah.
Well, but for 2D.
I mean, it doesn't mean that the continuum limit is not integral. I don't think it is, but.
Of course, yes. I mean, Lattice Yang which is believed to be nowadays due to some twisted Yukuji-Kawai, but still 4-matrix model is too complicated for integrability still.
So, people do lattice gauge theory and try to, for QCD, improve their lattice action.
Yeah.
So have you tried, I mean, presumably, you could apply this to any lattice action. Have you tried to play around with improvements?
Not yet, but the process should be straightforward. You just have much more terms in the loop equation. Yeah.
You jump immediately by very big
But-
lengths when you add.
No, I got it, but you immediately can choose it to improve the continuum limit. So with just one parameter, you can get rid of
Then you
first
have to
terms.
truncate it much earlier than do it for Wilson.
No, I understand, but they're presumably, if you're interested in the physical limit, in the end, there's probably some playoff between, those two factors. And it's unlikely that the one-cat model, the simplest Wilson, actually would be the obvious choice, probably not.
Only by the reason of we want to go. As
I got it.
Zechuan puts it, we go in levels. Like you vary once, you get the length say, +4. You get vary twice, +8, etc. But if you immediately jump by 8, you have to truncate, and then you lose a lot of information from this truncation. So it's not clear. Maybe you are right. Maybe.
Well, it would be simple to test with the simplest improved for action that gets rid of the first irrelevant term.
Maybe it's worth trying.
I'm not a great lattice expert, but there are lattice experts here. That, I think, was really a crucial point of getting these incredible, precise lattice results for masses.
Yeah, for Monte Carlo, certainly it was a great step forward. Here, it has to be seen whether it's advantageous or not.
Okay. Let's thank Zechuan again.